Hello, everyone, and thank you so much for joining us here tonight. My name is Heather Upshaw. I'm the Development Officer for Materials Science and Engineering, and it's my great pleasure and honor to be here tonight to introduce Professor Elsa Olivetti. Elsa is a professor in the Department of Materials Science, and she is also an MIT alumna herself, having received her PhD in the department under Professors Don Sadoway and Ann Mays, studying composite materials for rechargeable batteries. She then went on to do a postdoc with Professor Joel Clark, who was one of the pioneers of material systems research. She joined the faculty in 2014 and currently holds the Esther and Harold Edgerton Career Development Professorship. And just last week, she was honored with a McVicker Faculty Fellowship, which is the Institute's highest honor for teaching. Elsa's research focuses on the environmental and economic impact of materials choices on a global scale, touching on subjects from cobalt usage for batteries to end-of-life recovery of post-consumer plastic waste. Elsa is joined tonight by Basui Ravi, who is a doctoral student in her group. Basui did her undergraduate degree at IIT Bombay before coming to MIT, and she's studying the cost and benefit of end-of-life options for plastic waste in the United States. Tonight, Elsa and Basui will be discussing a few examples of the way that materials choices will impact our climate mitigation strategies. So please join me in welcoming them. Thank you, Elsa.
Excellent. So we'd like to talk to you today a bit about greenhouse gas emissions outside of the electricity sector. And the reason for this is if we look to total US CO2 emissions in gray, this may be coming down, but that seems to be a reduction in the impact of electricity generation shown in green. But the other piece of that graph is industry, which is flat and maybe even growing. Much attention has been focused on reducing greenhouse gas emissions in the electricity sector due to the use of buildings and the use of vehicles. And this attention is well placed, as we see on the pie chart there on the right, where emissions are dominated by those end use of buildings and vehicles. But as much as a third comes from industrial materials production as well. This is a harder area to decarbonize because there's not only the energy required to reach high temperatures, apply pressures, or undergo separation processes, but also direct emissions associated with the chemical processes themselves. This impact is even more dominated by a few key materials, metals, cement, and chemicals, which are precursors to polymers. So if we don't move the needle on those materials, we can't reach the needed targets for reduction. And there are a couple of strategies, and we're going to focus on that part of the pie today, what we can do as an engaged, solutions-oriented community. There's basically two ways to reduce this impact. The first is the quantity we use, which is expected to continue to rise as estimated on the left there for plastics. So we need to shift that overall piece of the pie down. And the way to do that is enabled by materials efficiency strategies. You see a couple of those listed here, and an effort that I was involved with the United Nations quantified the potential for each one of the strategies I'm showing and their potential to reduce impact. The most compelling one we found was actually more intensive use, which is something like the square foot per person that you live. And at first I was sort of disappointed. We can't engineer our way out of this problem, but this points to factors that are under our control now for transformative behavior change. So these are actions we can directly take. And so my first point to us all is to live more intensely. And another option is not only about the quantity, but about the impact per unit emission. So an energy or CO2 emissions per unit impact. And I'm showing that on this plot here, where with the materials that I'm interested in shown in the circles on the side. So in order to reduce those emissions, here we can look to technology development. And that, my second point, you can help move forward by electing officials who support relevant policies, such as pollution controls with trade measures, clean manufacturing demand pull and supply push, and investment in infrastructure that supports industrial transformation. And just to give you a little bit of an insight into this, I'm showing you two examples of technologies at MIT. One is the electrification of the production of steel through electrolysis. This strategy eliminates CO2 that's released in the early extraction steps by using electrons instead of carbon to perform this reduction. There are other benefits to this technology, such as more modular design that can be distributed right at the mine. So that's one option in our big pie that I was talking about before. For cement, we can look to alternative inputs that lower carbon dioxide emissions because they eliminate the CO2 producing calcination of limestone, alternative inputs such as waste materials. But the challenge here is nobody's trying to make a waste. So we can't really rely on one stream as a feedstock if we want this approach to be massively scalable. We have to be flexible and robust as feedstocks change. And so this is an example of the third point that I want to get across tonight. And that's about complexity and the complexity of the opportunity. So if we're thinking about replacing the incumbent CO2 producing Portland cement with a variety of alternative feedstocks that reduce emissions, we might look at natural materials or we might look at waste materials. But use of any of these materials is not inherently sustainable. We have to think about the quantity and quality of that supply because it's a waste, it's a secondary source, and that presents challenges. And so one option we've pursued in my lab to look at CO2 reduction in cement is working with a community in northern India to look at alternative feedstocks from agricultural wastes to make building materials. And so here, this alternative cement derived from our approach addresses challenges both in waste production, lowers the energy of production, and also CO2 emissions. And we've been scaling and extending this approach. But the complexity was to make the formulation that's robust to the changing conditions where these wastes are produced. Another alternative feedstock consideration that we are all very familiar with is using secondary or recycled materials. And I always say that the answer to all questions around whether recycling is environmentally beneficial is, it depends. And here's a story where it's particularly complex for plastics.
It is indeed complex, and I'll spend a few minutes talking about why that is so. Today, the life cycle of plastic products is overwhelmingly linear. Most plastics are produced, used, and disposed of in landfills or incinerated. This means that along with the material, all the energy and resources that we put in to produce the product is wasted as well. What's more is that the production of plastics has been exponentially growing ever since large-scale manufacturing of plastics began in the 1950s. This growth is alarming. Under current rates of waste generation, by then mankind would also have landfilled 12 billion metric tons of plastic waste, enough to fill about 40,000 football fields to the brim. The question that many have been asking is, does it have to be this way? There is no doubt that plastics continue to be incredibly useful. And while Elsa pointed out, reducing and reusing them as much as possible should be our primary goal, eliminating them completely is not something we can afford to do in the short term. So we still need to think about what to do with them at end of life. And with that in mind, I'd like to take you through a brief review of what we can do with plastic waste and what practical and technological challenges they pose. So first, thermoplastic waste can be mechanically shredded, melted, and reprocessed into essentially new plastic products. This is what is meant by recycling in the general sense. This is most likely what's happening to the PET bottles you consciously throw in the recycling bin. Next, what we can do is we can go one step further back and chemically depolymerize the plastic waste into constituent monomers, which are like the building blocks for polymers, and put these monomers then back together in the same or a different fashion. Finally, we can go even further upstream and pyrolyze the plastic waste all the way to fossil feedstock that can then be upgraded to fuels. And so while we can do all these amazing things with plastic waste, the catch is collecting and sorting it, and the economic and environmental cost of doing so. Think about all the plastic waste and packaging you encounter in your daily life, and then think about how different they look and feel. Even if we use plastic as an umbrella term, it covers a diverse number of materials with varying properties. What's more is that when you put them in the trash can or recycling bin, they mix and contaminate each other. Let's think of a few more concrete examples in our everyday life. The fact that all these are made of different plastic types is just the beginning of a complicated problem. The green PET bottle may have chemicals added to impart color that can contaminate the more transparent bottles. Films cannot usually be recycled because they get entangled in the machines at the sorting facility. Think of the takeout container. The optical sorting machinery used to differentiate polymers is blind to black color, and therefore is unable to sort it. And your chips packet that looks like a thin sheet has many sheets of different materials laminated together, and separating them is extremely difficult. These are just a few examples from food packaging, things most of us have in our kitchen or pantry, and you can already begin to appreciate how challengingly diverse this waste stream is. This diversity will only increase as time passes unless we do something about it. We have to acknowledge that the diversity of plastics that makes it a problem at end of life and the versatility that makes plastics so terribly popular for all types of applications are just two sides of the same coin. And the complexity that stems from this diversity or versatility takes many forms, from the choices made at every stage, as well as trade-offs that these choices present, from the monomer to the polymer to the processing of the product, from the molecular scale to the system-wide infrastructural scale. And this very multifaceted complexity is what makes this problem intriguing to us. What I like to do is look at different economic and environmental impacts of these different choices at different scales and stages to reliably evaluate how to move the needle on the plastics problem and sustainability. I hope with these examples of metals, cement, and now plastics, Elsa and I have been able to give you a glimpse of some challenges in the materials space and how we need to address impacts across the entire life cycle.
Great. We've got a couple of good questions coming in here. So one question that came in was about cement and steel and the sort of maturity of those industries. And I think one thing that we found, they're kind of, these alternatives can take a couple of flavors. One is looking to the incumbent technology, as displacing the incumbent technology. And so the example that I gave in steel and electrification of steel, the startup out of MIT is called Boston Metal. And not only are they offering a CO2 reduced option, part of the business strategy is that modularity that I mentioned, where they could be right at the mine site. And so there is competitive from these new, there is competition to these sort of incumbent materials, where they need to offer not only cost-effective alternative, but something in terms of the logistics and the sort of the ways in which the technology is applied. And the other kind of example I see, which I see more often in cement, is some of the really big mature companies kind of taking those technologies and testing them in-house. So LafargeHolcim, which is actually a member of the Climate and Sustainability Consortium that MIT has just launched, they've been looking at these CO2-free options as alternative products that they can charge a premium for. So in that case, they're working with these sort of small startups to embed those into their businesses. So that's sort of two options in terms of the kinds of pursuits that we see in the case of cement and steel. And another question that came in was about, in a related way, was about replacing coal in the steelmaking process, and the timeline for that. So that's related to the point I was just making around kind of the maturity of those industries. And so you can think about coal reduction in a couple of different ways. The example I gave was changing the chemistry itself, right? So instead of a carbothermic reduction where we're using coal, now we're using electricity, and that's got a time horizon of the technology is in sort of prototyping and scale up phase right now. If we're talking about kind of this alternative raw materials option that I guess that I gave, where we're replacing coal with something like biomass carbon or charcoal as a reduction agent, that's a much further afield opportunity, and also really challenging because of the kinds of trade-offs that we sort of alluded to throughout around land use and other kinds of challenges in terms of having those really be scalable options, I think.
Yeah, that's a good point. And I got some questions on, are biodegradable plastics a viable solution? So that's a very interesting idea. But there are several challenges to biodegradable plastics, notably the fact that we want those same biodegradable plastics to be competitive with commercial plastics, not only in cost, but also in properties. So you have to think that you want it to be both robust enough to be able to displace the commercial plastic. At the same time, you want it to not be that robust that it can degrade in the environment without persisting there for decades or centuries. So it's been hard to engineer that type of material, and I think that's one of the reasons that we see sub 1% of plastics are biodegradable, or actually even bio-based or biodegradable. So yeah, it's definitely not a viable solution yet, but we should be looking into that.
And maybe another challenge with the biodegradability piece, Vasui, is this: do we have the right infrastructures in order for that degradation to occur? If we're thinking about it from like a compostable sense, right? That's something we all often think about, is if we have a composting alternative, where is this kind of infrastructure, the systems infrastructure, to actually have that composting and biodegradation occur? So there's something about not only developing the technology, but understanding the system in which it's going to operate in order to see if it's actually a viable.
Yeah. Another interesting question was about what processes are available to recycle plastics down to raw feedstock. There are many, and they're usually classified as pyrolysis or gasification processes, where you try to burn plastics in the absence of oxygen. Well, burn is probably not the right word, heat it to a temperature of like 400 degrees Celsius or something like that above its melting temperature. And you can see that it sort of depolymerizes, and you get something like C3 to C10 or maybe C20 hydrocarbons, but it's a mixture. And the problem is then separating it and then trying to purify it and getting it to a point where it's usable rather than just this raw feedstock. And you have to also understand that going back, if you're trying to go back in that sort of linear chain, you're expending more energy, and then trying to go back or go front, I guess, is you're expending even more energy. So it becomes a question of how much energy are we willing to put into the system? Is it better to then just let plastics degrade or incinerate or landfill? So there's a trade-off there.
Yeah, any of these sorts of, kind of newer technologies on the sorting side, whether or not it's things like plasma waste conversion technologies or even use of automated robotic techniques. There's some questions coming in on that. There's this balance of the sort of added costs of that and the yield of what that would enable when we're talking about these commodity materials, right? When we're talking about things like lithium batteries, where there is a lot of complex assembly processes, that makes the automated processes potentially more beneficial. It also makes the technology behind the robotics more complex versus if we're looking at something like plastics, or we've looked at also in the group at paper recycling, those, the kind of boundary between whether or not it's secondary or primary feedstocks make sense, the difference between those is small. And so anytime you have a difference between those, both in terms of the price spread, but also in terms of the environmental benefits, if you're adding a lot more engineering on the recovery side, you kind of swing to that other it not being as environmentally beneficial as Vasui just indicated. So I think that's one of the challenges with using more advanced techniques with these more commodity-like materials, and the kind of the complexity of the packaging that we mentioned in like the potato chip bag, that it's not priced according to the technology that's associated with that packaging. So that's challenging.
Yeah, another interesting question was, could we somehow modify the types of plastics produced so we could put them more easily into the circular economy? And this is to the point that the difficulty is that there are many types of plastics. And I think yes, the answer is yes, but we have not been looking at it from that perspective for the longest time. The plastics have been around. Recyclability has not been an inherent parameter for design in this space, just because plastic is so cheap to produce and so easy to manufacture at large scale, that this has never been more, I guess this has never been an important parameter that people try to optimize for. And so I feel like going forward, if there's enough push by consumers to want that type of feature in their products, then there would be more innovations in that space in trying to optimize it for recyclability and circular economy.
Yeah, great. There's a question about the alternative cement or alternative binder materials I mentioned with the case right at the end in our group, and about kind of how close it is to commercial scale. So we're, in terms of the particular technology that we've been working with this community in India I mentioned, we're implementing that technology through an NGO in the area. And what we're interested in doing is kind of expanding that approach, I guess, is where you have this kind of locally optimized solutions to alternative binders based on the wastes that are available. And that's actually an idea that's also taking shape in the United States as well, particularly in our world of very data-driven activities, right? There's lots of startups in the area of advanced cement mix design, cement and concrete mix design based on using data-driven approaches. And that's not necessarily CO2 driven, that's driven around cost and flexibility to local materials, because cement and concrete are such commodity materials, you don't want to spend a lot of money driving them around. But there's also benefits in possibly using that to lower CO2, because if you can have the right mix for the right application, both in terms of water use, in terms of the use of supplemental cementitious materials, like I was talking about, alternative feedstock materials, that's another opportunity. So I think that in terms of the commercial scaling of that, using supplemental cementitious materials has been used in for a long time, right? We hear about coal fly ash or blast furnace slag, but particularly trying to make these kind of locally contextually appropriate use of alternative materials to lower CO2. That's something that started to take more shape, particularly as we're more interested in data-driven approaches to these things. Yeah, and there's a question here about commercially viable processes about depolymerizing tires. And yes, there's a faculty in chemical engineering, Brad Olson, who has looked into this. And I think one of your colleagues is working with him. Is that right?
Yeah. They've been looking into that. And so the problem there is that rubber is cross-linked. So it's not as easy as thermoplastics to just melt it. So what you do is you have to shred it down and then mix it with some sort of additives and then reform it. So yeah, it's slightly more challenging than thermoplastics for sure.
Yeah, and I think there's another session in this breakout that folks could go to in the second session around thermosets and the recycling opportunity in those materials with Professor Jeremiah Johnson. So if folks who are interested in those alternative recycling approaches can look at that. Yeah, so the maybe last question here is around glass materials, and that is actually a really challenging material in terms of recycling, because there's not great end uses. We tend to, at least in the New England area, we tend to use glass as landfill cap, crush it and use it to cover landfills. A, the energy savings is not so great on the recycling side, and B, it's very heavy to be driving around. So that there aren't a lot of good options in the recycling of glass for sure. I don't know if you remember when we were looking into that kind of municipal solid waste more generally, if glass is something that we considered in the sorting model. Do you know?
Yeah, we considered that. It's just, for some reason, it's not economically viable for the MRF to be sorting glass in the current sort of climate, and most of them don't. It's also heavy to transfer, and then it breaks, and there's a bunch of problems there.
It's something to think about when we, sort of end of life of renewable energy technologies like solar cells and things like that, right? That are silica based, and kind of thinking about clever ways to cost effectively repurpose that material.
Yeah, for sure.
Great. Well, thank you so much, Elsa and Basui. It's been a pleasure, and I think that to our guests, you can see why Elsa is recognized as such a passionate teacher. So we're delighted to have her on the MIT faculty. You're welcome at this point to look at your schedules and jump to another session if you'd like. And thank you so much for joining us tonight.